Hi guys! In this video we're going to be looking at conservation of energy in collisions, condition of elastic and inelastic collision, energy lost in an inelastic collision, and we're going to finish with a summary.
So far we've seen how momentum is conserved in collisions, but now we're going to think about how energy is conserved in collisions as well. So total momentum must be conserved in a collision between two objects so long as no external forces act. So for example, here we have two balls that collide and they each have a velocity v1 and v2. And since they have a velocity, since they're moving, that means they have momentum. So their momenta are given by P1 and P2. So if we consider this as a system where there are no external forces acting on it, so the external force is 0, then this means that the momentum remains constant. So the total momentum P is given by P1 minus P2. And P remains constant if there are no external forces. It is also true that conservation of energy must apply, as it does in any situation. So, as we said, these two balls collide with speeds u1 and u2, and they then rebound with speeds v1 and v2. So the total energy must be conserved because we know from the conservation of energy that energy cannot be created or destroyed, only transformed from one form to another. So that means the total energy can't change. It can only have been transformed into other types of energy. So we know that from the conservation of energy, that if the total energy before the collision remains constant, then we're going to have the same total energy after. So the energy may have been transformed into other forms, however, the total energy is still the same. Before a collision, at least one of the objects will have some kinetic energy due to its motion. So for example, this car here is moving with a velocity v from right to left, and we know that a moving object has kinetic energy which is given by a half mv squared. So a half times its mass times its velocity squared. So that's the kinetic energy of this car. When the objects collide, this energy cannot be lost, but it can be transferred to other forms of energy. So here is our car with some kinetic energy, Ke, and after the collision, the two objects become stationary, which means their kinetic energy is now 0. However, this energy hasn't been destroyed, it's just been transformed into other forms. So for example, a lot of heat energy can be generated in a collision, and also sound energy, which is why you might hear a loud crash when two cars collide. This type of collision, where kinetic energy is transferred to other forms, is called an inelastic collision. An inelastic collision is one where the total kinetic energy after the collision is less than the total kinetic energy before. So for example, these two cars here that are colliding, before the collision they have a certain kinetic energy which is greater than 0. So if they're moving, they have a kinetic energy. However, after the collision they come to rest, which means their kinetic energy is 0. So this energy that they had before must have been transformed into other forms of energy like sound and heat, as we suggested earlier. It is also possible to have all of the kinetic energy before a collision kept as kinetic energy after a collision. So the opposite can also happen. So for example, here we can consider two balls that are colliding, and rather than assuming that all the kinetic energy is transformed into other forms, now we can consider a collision where all the kinetic energy is conserved. So after the collision, the two balls are going to move off with the same kinetic energy as before. So in this case, the kinetic energy is constant. This type of collision is called perfectly elastic. A perfectly elastic collision is one where the total kinetic energy after the collision is equal to the total kinetic energy before. So the kinetic energy hasn't been transformed into other forms. So going back to our two balls that hit each other and then rebound. So the kinetic energy that the balls have here is exactly the same as the kinetic energy here. So the total kinetic energy. The individual kinetic energy of the balls may have changed, but the total kinetic energy of the system is constant. So this is before and after our collision. So now that we understand what elastic and inelastic collisions are, let's have a think about the conditions needed for each type of collision. Many collisions are not perfectly elastic nor completely inelastic, so lots of collisions are somewhere in between. So for example here, two cars are about to crash and they each have some kinetic energy. And when they crash, they might not come to rest straight away, they might still have some kinetic energy. So for example, they might continue moving in this direction. However, the kinetic energy they now have is a lot smaller than the kinetic energy they had before the crash. So some of the energy must have been transformed into other forms. However, not all of the kinetic energy has been transformed into other forms. For example, when a car crashes into another car and sticks, there is some loss of kinetic energy to heat and sound, but not all kinetic energy is transferred away. So for example, after these two cars collide, they're still moving off with some velocity v. So they still have some kinetic energy. However, because this kinetic energy is less than the initial kinetic energy before the collision, this tells us that some of the energy must have been dissipated as sound energy and also heat energy. So these are generated from the crash. The cars continue moving at a reduced kinetic energy. So we say that the collision is inelastic. So the cars have lost some kinetic energy because before they were each moving with a speed u1 and u2. So this was our system before the collision. However, afterwards, although they're still moving off with a velocity v, their kinetic energy is a lot smaller. So some kinetic energy must have been lost. And since some kinetic energy has been lost, we say that this is an inelastic collision. Note that kinetic energy is a scalar quantity, so the directions of the objects in motion do not matter when finding total kinetic energy. So kinetic energy is a scalar. We don't care about what direction the velocity is going in when we calculate kinetic energy. We're only interested in the magnitude of the velocity. So going back to our two cars that are colliding head-on, they've got speeds u1 and u2, and they each have mass m1 and m2. So we can find the kinetic energy of each car before the collision. So for example, for the first car, we can say that ke1 is equal to a half m1 times u1 squared. And you can actually see that because we're squaring u1, even if we were interested in the sign, that squaring would remove the sign anyway. So this reinforces that kinetic energy is a scalar quantity. So then we can do the same for the second car. So ke2 is going to be equal to a half m2 u2 squared. So we can conclude from this that energy is a scalar and the kinetic energy is always positive. And we can therefore write an expression for the total kinetic energy of the system, because it's just going to be the sum of the two individual kinetic energies, since we've said it's scalar and they're positive, so we're not interested in signs. So this gives us a total kinetic energy of a half m1 u1 squared plus a half m2 u2 squared. So that's an expression for the total kinetic energy of the two cars. To work out whether a collision is elastic or inelastic, we start by calculating the total kinetic energy before the collision. So here we're considering the kinetic energy before. So each ball has a mass m1 and m2 respectively, and velocities u1 and u2. So those are its initial velocities. So we can find their kinetic energy before the collision, ke1 and ke2. So the total ke before is going to be given by the sum of ke1 and ke2. and we've just found an expression for this. We said it's equal to a half m1u1 squared plus a half m2u2 squared. So that's our total kinetic energy before the collision. We then calculate the total kinetic energy after the collision. So now we're looking at after the two balls have collided. So their mass hasn't changed, they've still got mass m1, m2. However, now their velocities may have changed. So we've got a velocity v1 and a final velocity v2 for the two balls. So the total kinetic energy after is given by the sum of the new kinetic energy. So we've got new ke1 plus new ke2. So these new kinetic energies are determined by the new velocities of the balls. So this is equal to a half m1 v1 squared now, so we're using the final velocity, plus a half m2 v2 squared. So that's our total kinetic energy after. To figure out whether the collision was elastic or inelastic, we then compare these total kinetic energies. So if the total kinetic energy after is equal to the total kinetic energy before, so we then know that we have an elastic collision because all the kinetic energy before the collision has been converted to kinetic energy afterwards. However, if the total kinetic energy after is less than the total kinetic energy before, then we know that some of the kinetic energy has been transferred into other types of energy like heat energy or sound energy. So therefore, this will be an inelastic collision. For example, consider two objects of mass 2 kilograms moving towards each other with kinetic energies 9 joules and 16 joules. So we've got two objects, masses 2 kilograms each, and we've been told that before these two balls collide, so they're moving towards each other with a certain velocity, we're not interested in that. We've been told their kinetic energy. So this ball has kinetic energy 9 joules and this ball has kinetic energy 16 joules. When the two objects collide, one of them becomes stationary and the other bounces and moves at a velocity of 5 meters per second. So now we can look at what happens after. So the masses of the two balls don't change, they're still 2 kilograms. However, one of them is now stationary, so it has 0 velocity, whereas the other one moves off with a velocity of 5 meters per second. So we can find the total kinetic energy before the collision. So we just add together our two kinetic energies for this. So Ke before is equal to 9 joules plus 16 joules. Those are the two kinetic energies of the balls before the collision. So we have a total kinetic energy before of 25 joules. We can also find the total kinetic energy after the collision. So the kinetic energy after the collision is going to be given by the kinetic energy of the ball that has a velocity 5 meters per second, because the other ball is stationary, so that has no kinetic energy. So the kinetic energy after is therefore given by a half m1 v1 squared, and that's the kinetic energy of the moving ball. So we can therefore calculate the kinetic energy after. So the kinetic energy after is given by the kinetic energy of the moving ball, and that is equal to a half times 2 kilograms, because that's its mass, times its velocity squared, and its velocity is 5 meters per second after the collision. So this gives us a kinetic energy of 25 joules. So we can compare these to see if the collision was elastic. So we found that the Ke before the collision is 25 joules, and the kinetic energy after was also 25 joules. So the kinetic energy before is equal to the kinetic energy after. So we can therefore see that this is an elastic collision. So all the kinetic energy before has been converted to kinetic energy after the collision. So finally, we're going to consider the energy lost in an inelastic collision. We can calculate the amount of kinetic energy lost in a collision such as one where the two objects stick. So for example here, we have two cars coming towards each other. They've got masses m1 and m2, and initial velocities u1 and u2. So we can write an expression for their kinetic energy before. So each car will have a kinetic energy. So we've got KE1 and KE2. Both cars are moving. So the kinetic energy before is going to be given by the sum of these kinetic energies. So this is going to be equal to a half times m1 u1 squared, because that's the kinetic energy of the first car, plus a half m2 u2 squared. So that's the total kinetic energy before the collision. Now let's consider what happens after the collision. So the cars each still have masses m1 and m2. However, after the collision, they stick together and move off as one. So they move as one object. So now we need to get a new expression for the kinetic energy after. So the Ke after is going to be the kinetic energy of this whole object of the combined masses of the two cars. So that's given by a half times the mass of the two cars combined, so m1 plus m2, multiplied by their new final velocity squared, so v squared. And if we want to find the kinetic energy lost in this collision, we just do the kinetic energy before the collision minus the kinetic energy after. And then we can calculate how much energy has been lost. So let's look at an example calculation of this. A 1600 kilogram car travelling at 25 meters per second crashes head-on into a 1400 kilogram car travelling in the opposite direction at 20 meters per second. So these two cars are each moving at 25 meters per second and 20 meters per second respectively, and they collide head-on. If the two cars continue to move together in the direction of the 1600 kilogram car's initial velocity, how much of their total kinetic energy is lost in the collision? Notice here that lost is in quotation marks because technically the energy isn't lost, it's just transformed into other types of energy. So we've been told that the car travelling at 25 meters per second is the car with mass 1600 kilograms, and the other car has a mass 1400 kilograms. But the combined system of the two cars moves off in the direction of the initial velocity of the 1600 kilogram car, so they move off in this direction. So step one is to draw a simple diagram for the two objects. So we've said that this car here has a mass 1600 kilograms, this car has a mass 1400 kilograms. The 1600 kilogram car has an initial velocity of 25 meters per second, and then the other car collides with this car with a velocity of 20 meters per second. And then they move off in the initial direction of motion of this car here, the 1600 kilogram car. Our second step is to choose a positive direction for velocities. So we're going to choose the final velocity as the positive direction. So we can therefore draw this onto our diagram. So our positive direction is this one here. So this means that this velocity here is positive and this velocity here is negative because it's moving in the opposite direction. Step 3 is to write out the equation for conservation of momentum. So we know that for momentum to be conserved when no external force is acting on the system, the momentum before equals the momentum after the collision. Our fourth step is to write out the equation for momentum before the collision in terms of masses and velocities. So the momentum before the collision is just going to be the sum of the individual momenta of each car. So it's going to be m1 times u1, the momentum of one car, plus m2 times u2, the momentum of the other car. And this is because momentum is given by mass times velocity. Step 5 is to substitute our values for mass and velocity of the two cars into our expression for total momentum before the collision. So we can now actually find a value for the momentum before the collision. So we've got our 1600 kilogram car, which is moving at an initial velocity of 25 meters per second. And this one's moving in the positive direction, so we include a plus sign. then we subtract from it the momentum of the other car. The car with mass 1400 kilograms that's moving at 20 meters per second. And now the reason we're subtracting this momentum is because this car is moving in the opposite direction and it's moving in the negative direction. So if we calculate this, we get that the momentum before the collision is equal to 12,000 kilograms meters per second. Step 6 is to write out the equation for momentum after the collision in terms of masses and the unknown velocity v. So the momentum after is equal to the momentum of each car again summed together. So the masses of the car don't change. So for the first car, it's got mass m1, and we know it's got final velocity v, which is common to both cars. So when we write the momentum of the other car, we again write m2 times v. So the velocity is the same, which is why we can actually factorize this expression by taking the velocity out, and we're left with the sum of the two masses. And we can actually come straight to this expression because after the collision, we've said that the two cars combine. So they're one big object with a combined mass m1 plus m2. So we could have gone straight to this expression by saying their mass after the collision is m1 plus m2 and then multiply this by their velocity, which is v. Step 7 is to substitute our values for mass and velocity of the two cars into our expression for total momentum after the collision. So the momentum after is going to be given by the sum of the masses, so that's 1600 kilograms plus 1400 kilograms, multiplied by their common velocity v. So we end up with 3000 kilograms multiplied by v. And we've said that the momentum before the collision is equal to the momentum after. So we've said that the momentum after the collision is 3000 v. And this is equal to the momentum before, which we found was 12,000 kilograms meters per second. Step 8 is to rearrange for our unknown velocity. So to get the velocity v, we're going to divide the momentum by the mass. So we're going to divide 12,000 by 3,000. So we end up with the final velocity of 4 meters per second. Now we need to find the total kinetic energy before the collision. The kinetic energy before the collision is equal to the sum of the individual kinetic energies. So we've got a half times m1 u1 squared, so that's the kinetic energy of one of the cars, plus a half times m2 u2 squared, which is the kinetic energy of the other car. And now we just need to substitute in our values to get the kinetic energy before. So we do a half times 1600 times 25 squared, because that's the velocity of this car before the collision, plus a half times 1400 times 20 squared. So we then end up with the kinetic energies 500,000 plus 280,000 joules. So this gives us a total kinetic energy of 780,000 joules before the collision. So this kinetic energy is for the red car, which was the heavier car, and this kinetic energy was for the blue car. And step 10 is to find the total kinetic energy after the collision. So the kinetic energy after is given by a half times the combined masses of the cars. So a half times m1 plus m2 times their velocity after the collision, which is v squared. So now we again substitute in our values to get a half times 1600 plus 1400 times their velocity, which we found was 4 meters per second. So this gives us the kinetic energy after the collision as 24,000 joules. So step 11 is to now find the loss of kinetic energy due to the crash. So the kinetic energy lost is going to be equal to the kinetic energy before minus the kinetic energy after. So we found that the kinetic energy before was 780,000 joules and the kinetic energy after was 24,000 joules. So this gives us a loss of kinetic energy of 756,000 joules. Or we can say to two significant figures, this is 760 kilojoules of energy. So a lot of kinetic energy is lost in this collision.
Hey guys, I hope you enjoyed the video. If you're looking for an amazing A-level physics resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face and together let's make A-level physics a walk in the park.